We're going to continue here, number 27. Number 20 says find all discontinuities. So wherever the graph is not continuous. When is it not continuous? So we're talking about if there's a hole, an asymptote, a jump, one of those kind of things that's not continuous there. So we're going to go and look at each type of function we're given to know what are we looking for. So when we're looking at a rational, all we're looking for is at the denominator. And what we're looking for is the 0 in the denominator. So where is the discontinuity? So I'm going to write that down. Discontinuities, and at what value? So when x equals what, is it not continuous? So when I look at the denominator, is there any value x cannot be? So at x equals -1, it is not continuous, because when you plug in -1, there's no answer. Then the next part is, what type is this? So at -1, does the limit exist or not exist? Because if it exists, there's a hole or something like that that is removable where I can still evaluate, or it's non-removable. There's nothing that removes, and the answer is does not exist. So when I look here, look at the numerator and denominator. I can't factor here. In fact, when I plug in -1, I get -5/0. Clearly, does not exist. It is not indeterminate. A removable would give you an answer that is indeterminate. You might have to do more work to see if it's still removable or not. But here, clearly, if you get a number over 0, so a non-zero over 0, this is non-removable. There is an asymptote at -1. So again, what's one of the definitions we use for removable and non-removable? If it's removable, a discontinuity, it means the limit exists. So you can literally algebraically remove it from the function and plug in and get an answer. Non-removable means you can't remove it. And when you plug in, you get an answer that is undefined, and therefore it does not exist. So -1, I can't remove it. So when I plug in, that means this is non-removable. That also means the limit doesn't exist at -1. All right, 28. F at x equals 2x subtract 3. So know your functions. 2x subtract 3 is a polynomial, a line. A line is continuous everywhere. There is no asymptotes, jumps, holes, nothing. There's nothing that makes this undefined. The domain is all real numbers. Another way to describe it. Therefore, there are no discontinuities here. So this is smooth and continuous. 29. We have a rational, so we have to look at it carefully. So for this one, I'm going to factor the denominator so I can see it clearly. So if I look at this, I can see clearly that there are two discontinuities. So I'm going to write that down. Where do I look to find it? In the denominator. What x values make it 0? Well, -3, +3, both are bad. Why? Both give you the answer 0. So at positive and at -3 are discontinuities. Is there any way to remove them? Or if you plug in 3 or -3, do you get an answer that's indeterminate? There's no way to remove it. The answer is does not exist. The limit doesn't exist. So therefore, these are non-removable. Again, the calculus understanding of it is whether the limit exists or doesn't exist. So at +3 and -3, the limit does not exist. So therefore, it's non-removable. 30. Again, we have a rational. Again, I'm going to factor. Notice I have no limit notations because it's not a limit question. It's just talking about discontinuities. So factor out an x, just a common factor. And I want you to notice for the discontinuities here that the denominator, look at x. What value could I plug in for x that makes the bottom 0 altogether? So if it's just x by itself multiplying, then the 0 is 0. So when x equals 0, there's a discontinuity. But do you notice that x is removable? So I could remove x and plug in 0 and get an answer. fact, if I remove x and plug in 0, I get 1 over 1, and the limit exists at 0. Why does the limit exist at 0? Because x is removable. So this discontinuity is removable. Why? Because the limit exists at 0. How about the other one? So this is my little at symbol. So at x equals -1. So is there anything that removes -1 here in terms of x plus 1? So even though the x removes, x plus 1 does not remove. In fact, at -1, if I plug in, I get the answer -1 over 0. So this one does not exist. So because the limit doesn't exist at -1, this is non-removable. At 0, the limit exists, removable. -1, the limit does not exist, therefore non-removable. When I look at it, I can see x can be removed, removable. X plus 1 will stay there, so it's non-removable. 31. So step 1 is to factor. Now, I'm only looking at the denominator because that's what makes it undefined. That's what creates a discontinuity, is the denominator, not the numerator. So when I look here, look at the denominator only. So the denominator, the x value, there is a discontinuity. And the discontinuity is when x equals what number? Just look at the denominator. It's when x equals -3. Now, is there any way to remove x plus 3 so that the limit would still exist? So I could remove it, plug -3 in, and get an answer. So this, you can see, is removable. So if the limit exists, it's removable. If the limit does not exist, it's non-removable. So at -3, we could remove it and plug in. So it is removable, and we could still find the limit. Notice at -3, it's still undefined in terms of plugging into the function. But the limit exists, but the function value does not. 32. So f at x equals, and then x squared and x. Where are the discontinuities? So first of all, I look at each piece separately. Just x squared. Is there anything there that makes that undefined? No, it's a parabola, it's continuous. Just look at x by itself. Is there anything there that makes it undefined? Nope, it's a line, it's continuous. So the only part I need to worry about, is there a jump? So when I plug in 0 on top and 0 on the bottom, do I get the same y value? Does the limit exist at 0? And the answer is yes. In fact, when you plug in 0, you even get an answer. So in this question, number 32, there are no discontinuities. It is continuous. It is continuous because each piece is continuous, and then at 0, when I plug in, I get the same answer. So it's fully connected all the way through. There is no jumps. 33. Again, a piece-wise, look at each piece first. So if I look at the top piece and the bottom piece, they're lines, they're continuous. So I just need to look at +1. What happens when I plug +1 in onto the top? -2. What happens when I plug +1 in the bottom? +1. So if I ask you what's the limit as x approaches 1 from the left, you would say, oh, that answer is -2. If I said, what's the limit as x approaches 1 from the right, you'd use the bottom piece. That answer is 1. They don't agree. The limit does not exist there. Therefore, at x equals 1 is a discontinuity. No, it's not discontinuous. The limit doesn't exist, right? No, there's a discontinuity. So it's not continuous, there's a jump, and that jump creates it. So the function jumps from -2 and jumps up to 1 at when x approaches 1. So there's a jump because the top doesn't agree with the bottom when you plug in 1. So at x equals 1 is a discontinuity. And we say it's non-removable. Why is it non-removable? Because the limit does not exist. 34. So f at x, the two pieces are 2x subtract 5 when x is greater than 3. And then x squared subtract 8 when x is less than 3. So first I look at each piece. The top piece, continuous, line. The bottom piece, continuous, it's a parabola. But what happens when I plug in 3? So if I plug 3 into the top, what's the limit as x approaches 3 from the left? I'm not going to rewrite it all. So from the left, when I plug in 3, what's the answer? It's 1. What happens when I plug in 3 from the right of that same function? Plug in 3. What's 9 take away 8? It's also 1. So what did you learn about 34? And, oh, we got to be careful of this. Do you notice that one says greater than and the other says less than? There's none that says equal to. So this is when it's bigger than 3. This is when it's smaller than 3. But what happens when it's equal to 3? Well, we have nothing. There's a hole on both pieces. So at 3, there's a discontinuity. There's a hole there because neither piece is equal to 3. They both say greater than and the other less than, but equal to 3, we got nothing. So at x equals 3, there's a discontinuity. The question is it removable or not? So does the limit exist? Does left side equal to right side? So it does. So what do we say? What type of discontinuity is it? This is a removable discontinuity. Why is it removable? And the reason it's removable is because the limit exists. Because the answer is 1 on both ways. So what made this different than question number 32? When we went back, is that there's no equal part to the arrow. It's just arrow and arrow. There's nothing that made it equal to 3. 35. F at x equals x subtract 1. That's a line. Is there anything that would make that not continuous? Is there any domain restriction of any sort? Could you plug in any x value and get an answer? Yes. It's a line. It's continuous all the way through. There are no discontinuities for a line. Any polynomial, line, parabola, cubic function, all of them. It's continuous. No discontinuities. 36. Last question like this. Here we have a greatest integer function. Yes, we have discontinuity. These step functions have discontinuities everywhere. So at every time that's an integer. So at every multiple of 2, so 2, 4, 6, 8, and so on, anything that gives you the answer, that's integer. So only multiples of 2, when you plug in, give you the answer that's an integer. And the limit doesn't exist there because of the jump. So it's non-removable discontinuity. So at every multiple of 2, because only multiples of 2, when you plug in and reduce it down, give you an answer that's an integer. This is called a greatest integer function. $37. Use a calculator. I'll do it. Now, there's no button that says discontinuity, so we have to think through this. So, where are the discontinuities there? And the answer is it's a rational. So all I got to do is take the denominator equal to 0 to see what the answers are. So if I had this calculator, I'm going to show you first here. I'm going to press menu. I'm going to go to algebra, actually, and then zeros or solve. But let's say I wanted to find those. Let's say I wanted to know the zeros of the denominator. I would just type in 0, and I would just type in 6, the denominator only. 6x cubed, subtract 31x squared, plus 23x, plus 20. And I think that's all you need. Close it. Control Enter. Oh, it wanted to know the variables. So I'm going to have to go comma. For this, the comma is under pi. So find pi. Underneath is the comma. So I need to go comma and the variable, which is x, and then go Control Enter. And there's a few answers here. So if I look, there's negative 0.5. These are all discontinuities. If the bottom has an x value that makes it 0, it's a discontinuity. So where are the discontinuities? So when at x equals, and then look off your calculator. So negative 0.5 at 1.667 and at 4. So that's just looking off this calculator. I'll show you in Desmos in a second too. So that's just looking off this calculator. Now, I then need to know, is it removable or non-removable? Well, what's the only x value that makes the top 0? So if I took 10x equal to 0 and solve it, 0 makes the top 0. And it doesn't match with anything here. So if there's a 0 that matches, then it would be removable. But this is not removable. All of them are non-removable. So the limit doesn't exist at any of them. They're asymptotes at all of them. And nothing removes with the numerator. So if one of the answers was 0, I could remove it. But I can't remove any of these. So those are my zeros, and they're all non-removable. So if I went to Desmos, and all I want to do is type in the denominator, and that's what I'm going to do. 6x cubed subtract 31x squared plus 23x plus 20. And what I'm looking for this is where the zeros are. So look, where does it cross? The x-intercept. So negative 0.5, there's an answer. 1.667, got it. And the next one, at 4. So I just type in the denominator and find where the zeros are by looking at the x-intercepts, and I have the same answers that I just did with my fancy calculus calculator. All right, let's come back. So those are the answers for 37. 38. So this is x cubed plus 4x. So I'm just going to use x cubed plus 4x, and I'm going to make it equal to 0 and solve it. So I'm just actually going to use Desmos since I'm here. So let's go to Desmos, x cubed plus 4x. We can do that together. So x cubed, remember you can always press pause, don't forget that. X cubed plus 4x, and then when you're ready, press play, right? That's how these video things work. And then I look and make sure I zoom out enough that I can recognize that there's only one place on the graph where it crosses. There's only one x-intercept. So where does it answer 0? And the answer is 0. That's the only one. So let's go back here. So where are the discontinuities? And then the next part is, what happened with the numerator? What's that? Well, it's also 0. So therefore, both have the same 0 as an answer, which is 0. It's removable. In fact, if I factor out an x on the bottom, you get x squared plus 4. You can see the x's remove. And then you could plug in 0 and get the answer 4 as a limit. So the limit exists there. So this is considered to be removable at x equals 0. 39. So again, I don't need a calculator here, so I'm not going to do it. Where are the discontinuities? And you can see x divided by 4. I'm only looking at, and you can do, I think you can do a greatest integer function on Desmos. I'm not sure. So let me look to see if it's in the miscellaneous, maybe. Is there a greatest integer function there? It might be called a floor or a ceiling. So let's see if I don't know if it works or not. Oh yeah. So that ceiling is that you can see the steps, right? That's the greatest integer. Floor would be less than, but greatest than integer. You can see the steps here. And at -4, at 0, at and if we zoom in here, you can see what where are the jumps? -4, 0, +4, 8, 12. Those are all the jumps where it's not continuous. So that totally gives me a clue of knowing what it is. So where is it not continuous? So at every multiple of 4. What type of discontinuities are there? Because they're jumps, they are non-removable. Number 40, understanding discontinuities. If we have a function, f of x, you have x cubed and ax squared. I want to know what value of a would make this continuous. So you have a top piece that's continuous, a bottom piece that would be continuous because you have a cube function and a quadratic polynomials. What would make it continuous is if you plug 2 into the numerator, to the top function, plug 2 into the bottom, and make them equal to each other. So what a value would make it so that when you plug 2 in, you get the same answer. Therefore, continuous, there's no jump. So that's 8, that's 4, divide by 4. So you can see that when a equals 2, that is a continuous function. So when you plug 2 into the top and into the bottom, you would get the same answer. Done. 41. Similar question, but we have 3 pieces. That's just for your fun. So the top piece is x minus 1, ax plus b, and 2x plus 1. And then the top piece is valid when x is less than or equal to -1. The bottom piece is valid between -1 and 1. And the bottom piece is valid when x is greater than or equal to 1. So I have 3 pieces here. I want this to be continuous. So each piece by itself are lines. So I need to know what a and b would be so that when I plug in -1, so I'm going to plug -1 into the top. And when I plug -1 into the bottom, they have to be equal. So I'm plugging -1 for x, just using the top and the middle using -1. So I'm going to do that. So -1 take away 1 is -2. This is -a plus b. So I'll leave that be. Now the middle and the bottom, what do they share for that x value is +1. So now I'm going to plug in +1 into the middle and +1 into the bottom there. So now I'm going to use +1 to create a continuous function. I'm going to simplify it. That's a plus b is equal to 3. Notice the first one I came up with was -a plus b is equal to -2. And I want to solve for a and b to make it continuous. We have a system here. Very simple system, because if you add them together, the a's eliminate. You get 2b is equal to +1, so b is equal to 1/2. If I take that answer, I can go back and solve for a. So a plus b is equal to 3. Subtract 1/2, and you have your answer. So b is 1/2, a is 2.5, and with those values of a and b, it makes it a continuous function. 42. Now, these questions have to do with the intermediate value theorem, or IVT. Now, IVT says this. There are 2 conditions. Condition 1, continuous through the interval. So you're going to be given an interval. It must be continuous. There must be no discontinuities in that interval. Condition 2. That when you plug in the interval, so you'll have two, one's A, one's B, that what you're looking for must be in between those two values. So we're going to look at both. So we have to do condition 1, then do condition 2 to see if it guarantees a C value. So let's start. So f at x equals x squared plus x subtract 1. And it says f at c equals 11, and that's between 0 and 5. So step 1, look at the interval. Between 0 and 5, is this continuous? So the first question will be, is there any discontinuities here? Anything that would not make it continuous? Anything that's a domain restriction? The answer is no. It is a polynomial, it's a parabola, it's continuous everywhere. So continuous, yes. So condition 1, met. Condition 2. So first you ask yourself, is it continuous? Yes. Second, we're going to plug in 0 and we're going to plug in 5 into the function, the ends of the interval. So when I plug in 0, it's negative 1. When I plug in 5, that's 25 plus 5, 30. Take away 1, that's 29. So the second thing I got to know, does it meet the second condition? So it says 11. Because 11 is between negative 1 and 29, it meets the second condition. So the question is there a guarantee of a C? And the big answer here is yes. Now, if you sneak down to 47, it actually does the same question, but says, can you actually find the C value? So we're just going to combine 42 and 47 like one question. So is it continuous? Is that y coordinate that's given, is it in between the interval? Yes. So there is a C value that exists. So I'm going to take the function x squared plus x subtract 1, and I'm going to make it equal to 11 and then solve it. So I'm going to subtract 11. This is a quadratic. So subtract 11 and you get negative 12. Factor it. Two numbers that multiply to 12. Add to 1. So to factor it would be positive 4 and negative 3. When I solve this, one answer I get is negative 4 and the other answer I get is positive 3. Now look again. What's your interval? Interval is between 0 and 5. Are both answers between 0 and 5? And the answer is no. So why am I crossing this one out, negative 4? Because negative 4 is not in my interval. So what's the only C value that's in the interval? So what's the answer? And the answer is only 3, because only 3 is in my interval that satisfies it. All right, 43, and that connects us to 48. So 43, we have f at x equals x over x minus 1. At x equals positive 1, we have a discontinuity. So when I look at the denominator, positive 1 does that. So when I look at the interval from 0 to 2, right away it fails because it's not continuous. And if you look at it, they don't even want you to try to figure it out from there. So the interval is between 0 and 2. 1 is in that interval. And at 1, it's not continuous. It fails the first condition. The first condition is it must be continuous in that interval. It is not. So therefore it fails. It's not continuous. No C value. 44. F at x equals, we have a piecewise x is less than or equal to 1, 3, x is greater than 1, and then it gives us an interval. So first of all, it goes from negative 4 to 1. So the first thing I look at, is this continuous from negative 4 to 1? So when I look at negative 4 to 1, it's only the top piece. The bottom piece is when it's bigger than 1. Well, this interval does not care about the bottom piece. Only the top piece. And only the top piece, it is continuous. So, is it continuous? From negative 4 to 1. The answer is yes. Because I only have to look at the top piece. The next one, plug in the interval. So I'm going to plug in 1. I'm going to plug in negative 4. So if I plug in positive 1, I go to the same thing. So it's between 1 and negative 4. It's just x. So plug in, it's 1. Plug in negative 4. It's negative 4. The question says f at c equals... You know what I just did? I realized I did 45. My bad. Haha. I'm not going to redo it. It's 45, and then I'm going to go back and do 44. So 45. My bad. I totally like went boop boop because I was like, let's try this again. So for 45, this is not the interval. I'm like looking at the piece of paper. I'm looking at the wrong part of the question. This goes from 0 to 4. From 0 to 4, it involves positive 1. That's in the middle. So if I plug 1 into the top, I get the answer 1. 1 into the bottom, I get the answer 3. There is discontinuity at x equals 1. So when you plug in 1, you get two different answers, left and right. So it's not continuous. So it fails. No C value. Sorry. Let's go back to 44. Let's make sure I write it correctly. Dang it. There we go. 44. 44 is an absolute value function. Absolute value is continuous. It looks like a V. So condition 1, met. Make sure I write this correctly. Condition 2, I got to plug in negative 4 and plug in positive 1. And I need to know my y-coordinate that's given is in between these y-coordinates. So the absolute value of negative 4 is 16. The absolute value of 1 is 1. So when it says this is 3 in between that, yes. So both conditions are met. Take the absolute value of x and make it equal to 3. Solve it. The answer would normally be positive and negative 3. That's because positive 3 gives you the answer and negative 3 gives you the same answer. Both are correct. But look at this condition, this domain restriction. So what's the only right answer here? So the only right answer for C is actually negative 3 because negative 3 is in the interval. Positive 3 is a good answer for the equation but does not satisfy C because positive 3 is not between negative 4 and 1. So this was actually 44 and 48. We did two questions there. We did 45. I'm not doing it again. 46. And this connects to 49. So 46, f at x equals x squared plus x and x minus 1. And f at c equals 6, and it's between 5 over 2 and 4. So let's look carefully. There is a discontinuity. So at x equals positive 1, there's a discontinuity, right? Look at my interval. Is 1 in my interval? No. So in my interval from 2.5 to 4, we're good. So in the interval, there's no discontinuities. If positive 1 was in the interval, it would fail. The second part, I need to plug in. So I need to plug in 5 over 2. And I need to plug in positive 4. And know the answer is in between the two. So 4 is a lot easier, right? So that when I plug in 4, that's 16 plus 4 over 3. That's 20 over 3. Now 20 divided by 3 is like 6 and 2/3. That's going to be important because we got to have an answer between, in between where 6 would fit in there. So 6 and 2/3, we need an answer smaller than that. So I'm just going to like, hey, let's use a calculator just to get through this. So let's get rid of that. Let's say f at x equals, again, and type in x squared plus x over x subtract 1. 5 over 2. Too heavy lifting right now. So 5 over 2 gives you Oops. F at 5 over 2 gives you 5.83. Now, very close. But what I want you to notice is that 6 is in between there. Therefore, there is a value that exists because it's between 5.8 and 6. Both conditions are met. Continuous, and the y-coordinate is in between the intervals y-coordinates. That's the two things we're looking for. So we take the function x squared plus x over x minus 1, make it equal to 6, and solve it. We're going to solve this by multiplying both sides by x minus 1. Then we're going to distribute. Then we're going to make it equal to 0. So we're going to subtract 6. That's negative 5x. We're going to add 6. Then we're going to factor. Now, the two answers here in terms of factoring are, was it negative 2 and negative 3? So when I solve this, I get the answer 2 and 3. Now, when I look here for 46, look at the domain restriction again. So when I look at the domain restriction, this is 2.5 and 4, just so you know. 2.5 and 4. What's the only answer that's between 2.5 and 4? And the answer is this one, only 3. So what's the only C value there that we can find for the intermittent value theorem? And the answer is 3. That was 46 and 49. So we just did 49 too. So you can write down I did 46 and I did 49. 47 we did, 48 we did, 49 we did, 50. Two more left. So for number 50 says find an equation of the line that intersects that graph. So we have f at x equals, and we have x squared plus 1, x cubed plus 1. So this is when x is less than 1, when x is greater than or equal to 1. So we want to find it when x equals negative 2 and when x equals positive 2. So when x equals negative 2, it's only the top piece because negative 2 is less than 1. So just the top piece equal to negative 2, solve it. That means we're going to subtract 1. Now, make sure I'm doing this right. I don't need to make it equal to it. Haha, it's what x equals. So instead, it only applies to the top piece. So plug in negative 2, to the top piece, and find the y-coordinate that goes with it. So the question is, find an equation of a line. So what I just found out is x is negative 2. Y is positive 5, because I plugged it in only to the top piece. And what else do I need to know? I need to know the slope, right? In terms of that line that intersects the two. Well, the slopes can be found by the second one. So far I have this point, and that point is negative 2 and 5. Now the second one, x equals 2. Well, that only applies to the bottom piece when x is greater than or equal to 1. So I'm going to plug 2 into the bottom to get an answer. So if I plug 2 into the bottom, that's 2 cubed plus 1. That's 8 plus 1, which is 9. So positive 2 and 9. What I want is the line that goes through those 2 points. How do I do that? Now we can find the slope. So we know the slope formula. It's y2 minus y1, x2 minus x1. So subtract the y's and subtract the x's, basic algebra. That's 4 divided by 4, which is 1. So the slope is 1. So we can write down y equals, the slope is 1. So we don't even need the 1 there. Take one of the points. So if I took the top point, it would be x plus 2 plus 5. Now, if I did the bottom one, it would be x minus 2 plus 9, and it would be the exact same thing when we simplified it. But that is a beautiful answer. All right, last one. Number 51. It says, without using a calculator, classify if this is even, odd, or neither. So, a function is even when it has symmetry with the y-axis. Go back and forth in my head. Odd means it has symmetry with the origin. Now, I'll give you the most obvious examples. Y equals x squared is even. So when you look at the graph of y equals x squared, can you see that a parabola is symmetric around that y-axis? If I said y equals x cubed, that is odd, and a cube function goes up to the right and down to the left. So you have symmetry with the y. This is considered symmetry with the origin, where the cross coordinates have symmetry. But there's another way to tell when it's something not so obvious, and that's this, that you can substitute in. So let's say I choose to substitute in positive 1 and see what the answer is. If I plug in positive 1, the answer is 2 over 1, or 2. Now what would happen if I plug in the opposite of that, negative 1? Will I get the same answer? So if I plug in negative 1, all the even exponents make the answer exactly the same. This is an even function. That's just a quick test to see. Now, if I plug in positive 1 and I get positive 2, and if I plug in negative 1 and get negative 2, then that would be an odd function. And if I get gobbledygook, they don't match at all, and they're not opposite, then it's neither. So for this one, it's even, and you're done your assignment. I'm so proud of you. I know it wasn't short. I know it's good work, it's hard work, it's difficult work, all of that, and you're choosing to do it, and I couldn't be more proud. So this is Mr. G Math, over and out, and until next time.